I want us to focus on this diagram now. Okay, I want us to focus on this diagram. Okay, I want us to interpret this diagram. What does this diagram mean in detail? Okay, now first thing I want you to see, like what we have observed, right? So number one thing that we have observed from this, right? When shear force is equal to 0, okay, there's a possibility there is a possibility that bending moment is maximum. The emphasis over here, I highlight, is there's a possibility. So you have to check, because in this case, we have 2 points that the shear force crosses 0. We have to check which is the maximum. Okay. The next thing that I want to draw your attention is this. The next thing I want to draw your attention is this. When there's a point load, right? Point load only. So I want you to see between B and C, C and D. Okay, so I want you to focus on from point C, from point C to point D, right? So we only see a point load, right? Between that region C to D, there's only a point load distribution. So what do you realize about point load distribution is this: the shear force is a constant, and the bending moment has a gradient. Yes or no? Right? It has a gradient. So between this range, right? Between this range, right? C to D is a constant, and then it has a gradient, a straight line gradient. Yes or no? Right? And then when there is a distributed load, so you see we have a distributed load from point let's say from point A to point C, right? So between point A to point C, or to point C, yep. The shear force is a what? All right, the shear force is a gradient. The shear force has a, I think I have to put this, okay, has a linear gradient. And I think I have to put this also linear. Okay, a linear gradient. And what happened to the bending moment? Can anyone tell me? And the bending moment is a what? Is it a straight line? No, right? The bending moment is a curve. You can see that. Okay, so these are I'm writing out rules now. Okay, I'm writing out rules now. Okay, and then the next thing we can observe is what? Okay, so the another next thing is this. Okay, I want you all to see this, right? You can observe this part. So between A to B, right? The magnitude is negative. Yes or no? The magnitude is negative, right? The slope is also negative, right? Okay. Then we have another sector now. We have another sector. We have this sector over here. It is positive. The magnitude now is positive, right? The magnitude is positive. The curve down here, right? The curve up to here is also what? Positive, right? The highest polynomial is also what? Positive, right? Then when you come to this, when you come to the next one, right? This become negative magnitude. Then the curve, right? The curve has a negative what? Slope. And then when this is negative, the gradient is negative. So what I'm trying to tell you is this, okay? What I'm trying to tell you is this, is that when the shear force magnitude, or the shear force, yeah, magnitude is related to the bending moment slope or gradient. So i.e., so we have shear force, and then you have bending moment. Okay, you have shear force and bending moment. So when the shear force is positive magnitude, right, the gradient is also positive, right? As you can, as you can see down here, right? It's positive, right? The gradient is also positive, right? So this is positive magnitude, right? Then the slope down here is the gradient is positive. So what do I mean by gradient? If I draw a line intersecting over here, they're all what? Positive, right? And then over here between A to B, you draw the slope at a certain point is all what? Negative. Okay. So, and again, when it is negative magnitude, right? The bending moment, you have negative gradient. Okay, so that's the thing I want to emphasize. So these are the things that you can observe. Okay, you can observe from your shear force and bending moment diagram. Okay, so if we were to look at the deformation, okay, we look at the deformation pattern. If I'm going to sketch the deformation pattern, okay, so deformation pattern. By looking at the shear force and bending moment diagram, I can sketch how this structure will deform. Okay, so this is our point A. This is our point B. And then at a certain distance is point C and point D. Right? Like I mentioned before, if we look at deformation pattern, okay, if we look at deformation pattern, anything that's above 0, the deformation pattern will be smiling face. Anything that's below 0, the deformation pattern will be a sad face. Okay. So now if I were to sketch the deformation pattern, right, based on the bending moment, and we know that at a certain point down here, this is where your B goes to positive, right? So this is where the bending moment go positive. So it's going to start from sad face, okay, and then it's going to go smiling face, right? It's going to go smiling face, and then it's going to come back to 0. So this is how your structure will deform. So this is your deformation pattern, which we will do more. Okay, do more after your term test, right? Right. So the next thing, okay, the next thing we're going to do is how. Okay, so the next thing we're going to do over here is how to select the beam now. Okay. Okay, how to select the beam. Okay, how to select the beam. Right. So we know that our bending moment max, right? Our bending moment max is equal to 48 times 10 to the power 3 Newton meter. Okay, we know that value. Sorry, I'll make sure this page is bigger for you guys. Okay, we know that is 48 times 10 to the power 3. So the equation that we're going to use, and you guys have seen this before, is stress max, maximum stress, okay, or your allowable will be equal to N max, okay, Y divided by I. Okay. So all this is very obvious for you guys. Okay, you guys have seen this before. Okay, so if I were to draw a cross section, so this is a cross sectional view now. Okay, so this is a cross section view. Right, and I'm going to call, okay, where I, like I, you all know now, is the second moment of area. Right, and for this case, Y, okay, Y max is equal to C. Right, is a maximum point where you see the highest stresses. We know that. Okay, so this will be your Y max over here, and I'm going to let my Y max to be equal to C. Okay, so therefore stress max can be also be equal to M max divided by S. Okay, where S is equal to what? I over Y max, when it also can be equal to I over C. Okay, so I want you to pay attention. Why am I doing this for? What is this S? Okay, so if you look at the S, if you look at the units, so this is meter to power 4 divided by meter, so this is meter to power 3. Okay, so now let's go to the table. I'm going to pull the table up, so you guys will have this table also. I'm going to copy the table, and we're going to paste. Okay, where did the table go? The table is somewhere. Okay, so I'm going to make the table smaller so all of us can read. Okay, so for the term test, I will provide the table. Okay, so I want you to see this on the table, right? So some of you have seen this before, some of you have not. Fine, it's okay. So I want you to focus. The thing you have to relate is this diagram over here. Okay, the diagram and what all this over here means. Okay. So dependent on the type of shaft or the type of shape you use or destination that you use. So let's say we use W310X143. The area is 182 times 10 to the power 3. So the area will affect the what? Will affect the cost. Okay. In the